I'm Pranathi. Today I'm excited to walk you through my project where I developed a machine learning model to predict appendicitis. I'll show you how I built, tested, and evaluated my models using R. My project overview objective was to enhance the accuracy of appendicitis diagnosis through the application of advanced classification models. I used methods like logistic regression, random forest, and SVM, and the importance is actually to enhance diagnostic precision in medical practice. Overview of data. First off, let's talk about my data. I actually source my data from Zenodo, which is a public repository, and it includes clinical metrics necessary for diagnosing appendicitis. Let me show you how I loaded and first looked at this data actually. I use the basic read Excel function in my code. I can show you quickly. So this is how my RMD file looks like. I'll quickly run this chunk to load my libraries which are necessary. And this is how I have downloaded the data. And coming to the next step, which is the exploratory data analysis. Once I had my data, I started by exploring it. I looked at things like the number of missing values and the distribution of different features. And here's how I summarize this data and why it is important for my next step. The dataset actually includes a mix of numerical and categorical variables with 782 instances and 58 features with diagnostic results as the target variable, featuring varied distributions and several missing values. I strategically handled missing values and initially cleaned it. And next step is preparing the data for modeling. Before even doing that, cleaning the data was crucial, so I needed to handle missing values and ensure all data types were appropriate for modeling. Let me run through the code where I clean and transform the data, like converting categories to a format which my model can actually use. So I have removed these missing values and converted categorical data, and then I have normalized. I'm running the chunk now of my data preprocessing step. This is how I have normalized in the end all the code involving preprocessing. And my next step was to build my model. I chose logistic regression for its efficiency with binary outcomes, random forest for its handling complex data structures, reducing overfitting, and SVM for its strong performance with high dimensional spaces. For the training process, I partitioned the dataset into 80% training set and 20% testing data, employing tenfold cross validation to optimize model validation and prevent actually overfitting, ensuring robust model generation. And here's a quick look of how I've really built it. This is the splitting part, and I have implemented k-fold cross validation, so I have done hyperparameter tuning for logistic regression, for random forest, and for SVM. So I'm quickly about to run this code chunk. Yes, there you go. Now I have to evaluate my models. Evaluating my models is key to understanding how well they might perform in a real world setting. And I'm running it here in my code quickly. So while I run, I get this output. I have summarized my output here. the performance metrics are like this. The logistic regression model achieved an accuracy of 89.1% with my AUC metric of 0.8, demonstrating which is like a strong sensitivity and specificity. My random forest model outperformed with 93.5% accuracy and an AUC of 0.926, while the SVM model showed robust performance with 91.67% accuracy and AUC of 0.91. Coming to the comparison of my models, the logistic regression model exhibited an accuracy of 89.1% and AUC of 0.8, reflecting very good predictive performance. In comparison, the SVM model reached an accuracy of 91.67% and an AUC of 0.91, showing enhanced capability in class separation. And the random forest model achieved the highest accuracy at 93.5%, along with the AUC of 0.926. This indicates the superior overall performance in both classification accuracy and the ability to handle various data complexities. And now about my ensemble modeling. After evaluating each model, I combined them into an ensemble model. This method actually helps to improve accuracy by leveraging the strengths of each individual model that I've chosen here. Let's look at how I implemented the ensemble technique and observe the performance gain. Now I'm going to run this is how I have built the ensemble model. I've used the function called Predict Outcome class based on my individual models. I'm quickly going to run this. And I've got my output, and I've summarized my output in this way. So the performance of my ensemble model achieved an accuracy of 93.6% with an AUC score of 0.975, demonstrating its robustness and superior performance. And this indicates that the ensemble effectively integrates the diverse strengths of the individual models, leading to more reliable and accurate predictions. To quickly summarize all my whole project, building this ensemble model actually allowed me to achieve better diagnostic accuracy. And the key takeaways that I would want to talk about for this project is the ensemble model demonstrated superior accuracy that as we speak, and showed robustness, validating the effectiveness of combining multiple predictive models. Each model contributed distinct advantages, enhancing the overall predictive power is the successful aspect of this project. And I really faced a lot of challenges while cleaning the data. The main important the base of the project lies in how you pre-process the data, and I've really understood and learned so many other techniques and concepts which involves data pre-processing. So individual models varied in performance with issues like lower sensitivity in logistic regression and specificity concerns in SVM. All these things indicating room for optimization in feature selection and model tuning were some of my challenges also. And I think my future directions, there are improvements. There are always improvements. So my further refinement of hyperparameters, exploration of additional ensemble techniques, such as boosting, could potentially increase model precision and recall. And my next steps in research would definitely be integrating more diverse data sources, and advanced machine learning techniques like deep learning could be explored to address complex patterns in data and improve diagnostic accuracy in medical applications. Thank you for joining me in this walkthrough. I hope it gave you a clearer picture of how machine learning can be applied in medical diagnostics to save lives. Please feel free to ask me any questions or reach out to me in comment section. Have a great day. Thank you.